his dad. Oh, now I'm recording this. Never mind. I'm not going to say the sarcastic thing I was about to say. Anyway. Fool me once. Shame on you, internet. Fool me twice. Well, you're not going to fool me twice.
You could have stopped recording, say the thing that you were about to say.
No. Now it lives only in my brain. Little secret just for this guy.
Just write on that board.
No. So for you guys, this should be 3.4 because I added in that little stoichiometry practice, which is good. So we'll just change that here. Okay, so who changed my eraser? Well, that's stressing me out. Oh, it was you. That's okay. I wrote on my shirt for you. Anyway.
Someone changed your eraser.
It's okay. I'm not actually upset. It was a joke. Yeah, no, it's fine. It's all good. You've made beautiful art. I just want to make sure, like I said, this lesson should honestly take us 10 minutes and you can work on your assignment. But I want to make sure we're clear on it because it occurs to me that your assignment and even just that lesson on enthalpy I gave you assumes that you are comfortable with different representations of change in heat, right? So in a chemical reaction, the thermal energy included is part of the chemical reaction. If energy is released, then we need to say in our thermochemical equation that we get energy released. And on the other hand, if energy is absorbed, we need to say that energy is absorbed. And there's a few ways we can do that. And one of the ways we can do that is by including it right in the equation. So, for example, the molar enthalpy of the burning of ethanol is negative 726 kilojoules per mole, an exothermic reaction. And I want you to write a balanced thermochemical equation for this. I'm going to have you guys try this. And again, the reminder is that if something is exothermic, where should the energy live in the equation? It should be a product, right? Because if a reaction is exothermic, we're saying that it releases energy. So it's part one of the products. On the other hand, if the reaction had been endothermic, where would we include the energy? In the reactants. So I want you to try and write a balanced thermochemical equation for this reaction. The burning of ethanol. When we burn something, what are we reacting it with as a reminder? We require heat to get started. We'll talk about that in a couple days, but we're actually reacting it with oxygen. What will it form as its products, assuming it's a complete combustion? Carbon dioxide and water, right? As the oxygen smashes apart the ethanol, all the carbon will end up as carbon dioxide, all of the hydrogen will end up as water. Keep this up. This has gotten quite cold.
Did you change it?
I think so.
It was squared. This point.
We'll make it a point eraser in the tiniest one.
You can also draw something like on the bottom of the note, and when he scrolls down, he would have it drawn. I think we have.
What does he usually write in black?
Black or red.
And giant. Change all his pen sizes to be giant.
Do black first. Oh, it was Kayla.
Money doesn't grow on trees. Oh my gosh, I become my grandfather. Yeah. Oh, perfect. Oh, that's way better. Oh, I love that. Are paperclips still Pure steel, probably, right? Presumably. That's amazing. Oh, that's so much more fun. Oh, from now on. And it's going to be way less annoying to clean. That's tremendous. Huh. All right, team. What do you got for me? What's our reaction here? What are our reactants? What are we reacting? We have ethanol, which of course is... Okay. Did somebody just come up and change these now?
No.
I think you did. I think you did. And I think I'm going to fail you all. Just if you're wondering. If you're wondering who's going to fail as a result of this, that would be all of you. So where was I? Other than changing your grades, which I'm going to go do momentarily. Not funny, team. No, thank you.
It was not.
A little bit funny. Anyway, ethanol, what is it? Yeah. And you may want to just draw it, right? Like it may be helpful to you to be like, I know how to draw ethanol. So draw it. And as we draw that, we can say, okay, the formula is what? C2, H, 1, 2, 3, 4, 5, 6, and an O, right? Cool. And we're reacting it with oxygen. Good. You don't have to draw this, to be clear, but if it helps you to get the formula, then by all means. What are we going to produce as our products? All the carbon's going to turn into?
Carbon dioxide.
CO2. Very good. All the hydrogen's going to turn into? H2O, right? And then, how do I handle the energy in this case?
Plus 726 kilojoules.
Great. Now, do I have to put plus negative 726 kilojoules?
No.
Why not?
Because it's on the...
Yeah, that negative is telling us where it goes. So the negative is what tells us put it on the product side, right? So I just put here 726 kilojoules. Now, notably, we aren't going to put kilojoules per mole because the whole point of this is that it's 726 kilojoules per 1 mole of that, right? This balanced chemical equation says that this is 1 mole. If as I go to balance this, I had to turn this into a 2, what would I have to do with this number? I'd have to double it. Does that make sense? That number is tied to the number of moles of ethanol. Does that make sense? Now, as it happens, do we need to put a 2 in front of that to balance this one? How's this balance?
2 CO2 plus 3.
Yeah, if we look here, slow down. We have how many carbons here? So how many CO2s are we going to have to produce? 2. All right, let's do that. How many hydrogens do I have here?
6.
Each water uses how many? So how many waters do I need to take care of all my hydrogen? 3. And now, what's the only thing we have left to balance?
Oxygen.
Oxygen. Now let's be careful. How many oxygens do we have here?
3.
3 here, plus
4.
4, for a total of
7.
7. Okay. So we have 7 oxygens on this side. How do I balance that on this side? Oh no. Do I need 3.5 of these? No, why not?
But there's 1 oxygen there, so
We have 1 oxygen there. So how many more do I need?
3.
Well, I need 6 more, which I can get by turning this into 3. Very good. And now everything balances. If it's been a while since you've had to balance chemical equations, remind me, I can put you on the practice app for that. We can throw a billion balancing questions at you, give you practice like crazy. How's that feel? Not too bad? So that is one option. We can include the energy right in the equation. And you've seen that, right? Cool. The other option is that we just write the equation. And then, on the other side, we report the delta H value. Does that make sense? This is the other thing you will see very often, where they write a balanced chemical equation. They don't include the energy in the equation. Instead, next to the equation, they just say delta H equals, and they write the enthalpy change there. That's the other way we can do it. So we wouldn't put it in the reactant side. We wouldn't put it in the product side. We put it over next to the equation, and we write it delta H equals whatever it is. In this case, Sulfur dioxide and oxygen react to form sulfur trioxide. The molar enthalpy for the combustion of sulfur dioxide is negative 98.9 kilojoules per mole. What's the enthalpy change for this reaction? Just write the whole reaction out. I shouldn't even, this is not the question I meant to ask. I should say, what is the way to write this? I got to change that in my master note. Did you get a copy of this today, kiddo? Yeah. Brand new. It's right here. Yeah, it's right here. It's just new, so you wouldn't have had it previously. So just write this out. I want to basically see, can you write the balanced chemical equation? What is the chemical equation here? Sulfur dioxide reacts with oxygen. Give me that. What's sulfur dioxide? You okay? Okay, I got you. Give me a second. All right, so what's the formula for sulfur dioxide?
SO2.
SO2. Good. I'll come pick those up in a minute. Don't worry. Okay. And what's it reacting with? Which is O2. What's it forming? Sulfur trioxide. SO3. Okay. Is this balanced? How do you balance it? Yeah, we don't like the fact that this is an odd number makes this challenging. Whenever you have an odd number, what's a good idea to put in front of it? 2. That'll make it an even number. How many oxygens do we have now? Great. So how do I make this 6 oxygens? 3 in front. And we're almost, except I already have some here. So let's hold off on that. How many sulfurs do I have here? 2. How many do I have here? So what do I need to put in front? And now I have 2 sulfurs. How many oxygens do I have? Compared to, meaning this 2 gets us there, right? So that's balanced. How's that? Great. Now we have to be careful because if I were to include, can I show you something? Look at me. Don't write. Everyone put the pencils down. Put the pencils down. Do you promise? Put them down. If I were to include this number here, would I put it on the reactant side or the product side? I would put it on the product side. Okay, but here's the thing. Could I put it as 98.9? Again, don't write this. Do not put your pencil down. Put it down! Thank you. Could I put it as 98.9 kilojoules? Why not? What would I have to put it as? I'd have to multiply it by 2 because we're doing the reaction twice. Does that make sense? So sometimes, then I'd have to work that out. That would be 187.8 I'd have to put here, right? 187. Yeah, something like that. Anyway, point being, I don't have to do math. What am I, a math teacher? No. Not a real one, that's for sure. Anyway, so listen, instead of doing that math, we can just come to the side and we can just say delta H equals negative 98.9 kilojoules per mole. And now it doesn't matter how we had to balance that out. Does that make sense? We can just say that for every one run through this equation, it releases that much. And then if I go to do my stoichiometry, no problem. If I'm referring to the SO2, that's going to get doubled, right? If I'm referring to the O2, it won't, whatever. But we can just report it as per mole on the side, no hassle. This is the way you will see it most often. More often than not, when they put the enthalpy change in a reaction, they just write it on the side. They say delta H equals whatever per mole. This is the most common representation. Yeah? If we doubled this. Yeah, if we doubled this, we would then have to double that. But the whole point of this is that we don't have to do that. That's why this is a preferred way of writing it out. We can just say per mole And then we don't have to worry about multiplying it by 2 or multiplying it by 5 or whatever. We're just reporting it per 1 mole. So that makes this the kind of most common, the most preferred way of writing it. Does that make sense? Because that means if you had 6 moles of SO2, you would say, I have 6 moles of SO2, but I know that we get 98.9 kilojoules for every 1 mole of SO2. We don't have to worry about the fact that or for every, not 1 mole, I'd look at the equation, and I'd say in the balanced chemical equation, we use 2 moles. Does that make sense? So when you have it this way, you can then just use the balanced equation the way you've always used the balanced equation. Does that make sense? So that is kind of our preferred method there. So we just write it this way. Is that cool? All right. And again, we've already said this a million times, but we'll just say, don't forget, for exothermic reactions, delta H is negative. And for endothermic reactions, delta H is positive. Good. All right, we want to make sure we're keeping that straight. Exothermic is negative, endothermic is positive. There is a third I'll give you a minute to write that. There's a third representation we sometimes use, which is we will sometimes draw what's called an energy level diagram. Now, you're not going to do this to solve most questions, but it sometimes is helpful as a conceptual piece, and of course, you'll sometimes come across it in questions. So I want to make sure you're familiar with it. An energy level diagram is a graph. And it's a graph where on the bottom, I hate you all, is time. In other words, the extent of the reaction as time goes forward. It doesn't have to necessarily be measured in any unit. Could be seconds, could be minutes, could be hours. Depends on the reaction. Could be millennia. And then on this scale is enthalpy, right? In other words, H, and that's measured in joules or kilojoules or whatever. Doesn't matter what. And in this example, what we see is that the reaction starts off with a certain amount of enthalpy, right? So the energy inside the compound starts out up here, and then over time the reaction happens, and by the time we have all the products, in this case, is the amount of energy inside the products more or less than what was in the reactants? Less than. So what kind of reaction is this? If the products have less energy inside of them than the reactants did, what kind of reaction is this? Exothermic. It lost energy. And of course, if it lost energy, if I were standing around this reaction, what would I physically feel? You'd feel heat. You'd feel warmth. Very good. So this is an exothermic reaction. Hello, come on in. Oh, that's really sweet. Hi, guys. Hi, I'm good today. I made my own, but thank you so much. You're welcome. So this is an exothermic reaction. Energy is released. Now, interestingly, we don't actually know these values here, right? Like, we don't know the total internal energy of our reactants, and we don't know the total internal energy of our products. But what we do know is that the difference between them we call, what do we call the difference between the internal energy? Delta H. No, if you want to know delta T, that would be the time it takes for the reaction to happen. That would be delta T, but we don't care about that. I mean, we're going to care about that in a few days, but right now we don't care about that. Yeah, you're going to be doing full-on graphing, team. Who's ready for quadratics? Who's ready for cubics? Who's ready for 1 or 2 quartics? Don't worry, we give you cheats. Well, you tell me, what's a quartic? Y equals ax plus b is a linear relationship, right? Y equals ax squared plus bx plus c is a quadratic relationship, which is a terrible name. Objectively, it's a terrible name, right?
Quadratic?
Yeah.
Well, we discussed the alternative. Because, cube, cubic.
Yeah. Squaric.
Square.
Squaric. Squaric is clearly better.
Squaric, yes.
Squaric.
Let's say it right.
Squaric. It should be a squaric relationship. A cubic is ax cubed plus bx squared plus cx plus d. And then a quartic is ax to the fourth plus bx cubed plus cx squared plus dx plus e. So yeah, welcome to chemistry, team. Get excited. We're doing polynomials.
What's a cardic?
I'm recording, so I'm going to reserve comment. I'm kidding. I love Kartik. What about this reaction? I hate you all so much. Oh, I hate you all. Okay. Time and enthalpy. What about this reaction here? Obviously, we have an energy level for the reactants, an energy level for the products, and what are we noticing? The internal energy of the products is higher than the internal energy of the reactants. It's going up. We have more energy inside the compounds. If you put your hands next to this reaction happening, what would you feel? Don't answer. Just think. Right, now someone can answer. What would you feel? You'd feel cold, right? Because if the products are absorbing energy to form, then they have to get that energy from somewhere. They're going to get it from the surroundings. So this reaction is going to cool down. Now, to be clear, this reaction might happen at high temperature, but the point is it's absorbing temperature. It's absorbing temperature. That's not a thing. It's absorbing heat. It's absorbing heat energy. Oh my. So what do we call that kind of reaction?
Isn't enthalpy in kilojoules?
It's in whatever you want to be in. It could be in calories if you want. It could be in kilowatt hours. The kilojoule is just 1,000 joules, right? So if something's in joules, it's also in kilojoules. It's just a measure of scale. Did that answer your question? We do most often use kilojoules, yes. But you'll see, again, if you look at old American textbooks, it's all calories. If you look at old British textbooks, it's all British thermal units. But it's all energy. Energy is energy. What do we call this type of reaction? Endothermic. Good. And an endothermic reaction is one in which energy is absorbed. And how would I find delta H on this graph if I felt so inclined? We could extend that line, and we could simply measure the distance between them, and the distance between them would be delta H. Now, if you look here, if we extend this line and measure delta H, H is going down. So delta H in this case will be positive or negative. This one here.
Negative.
It'll be negative because the amount of enthalpy is decreasing. So delta H is negative. What about here? The amount of energy is increasing, so the delta H is positive. Do you see how that can actually be kind of a useful representation? Where this graph can also be useful because it can give us more information. You don't need to know this yet, but we're going to look at graphs, and you might have one reaction that is an explosion. It goes like this. It releases that energy super quickly. Does that make sense? You might have another reaction that is gradual, but actually gives you the same amount of energy loss, right? This would give out just as much heat as that, only this might keep you warm for 3 days, whereas this might explode and destroy the building you're in. But it's actually the same amount of energy. Does that kind of make sense? When we start to work with these graphs, the thing we're eventually going to look at is not only the change in energy, but also the change in time, right? Which is important. A reaction that releases a whole bunch of energy at once is obviously very different from a reaction that slowly and gradually releases its energy. Does that make sense? You can have some reactions that release a tremendous amount of energy, but it takes them 1,000,000 years to do it. That doesn't feel like it's putting a lot of heat out to you, but it's actually putting just as much heat out as a thermonuclear bomb. It's just doing it slowly and gradually. Yeah. These would actually be completely impossible. There has to be some degree of slope. So yes, these wouldn't just be explosions. These would be like singularities. These would be like quantum events that occur instantaneously, which doesn't make any kind of sense. But they're for illustrative purposes. Yeah, in real life, there has to be a slope involved. They have to be what we call, does anyone know what you call this shape of curve? Mathletes? I don't actually know if we use it in math, but in science we do. We refer to them as sigmoidal curves. Is that a math term as well?
It's like an arctan.
Yeah, it's an arctan curve. But yeah, we typically use the term sigmoidal. Because they're shaped like the letter sigma. In other words, they're kind of shaped like the letter S. Anyway, sigmoidal sounds a lot fancier than kind of S-like, S-adjacent. That's the lowercase. Yeah. Yeah, right, of course. Right, just like that's uppercase delta. What's lowercase delta? It's just a D, right? Yeah, just a little D with like a... That is lambda. Well, lambda is like this guy, right? But what...
Yeah.
Delta is kind of D-like, isn't it?
Isn't it like a circle with a little cherry bomb?
Isn't that lowercase sigma? That's okay. Now we're gonna do it. Ready? Okay. Delta is obviously that. Delta is that.
That's it.
Yeah. And then sigma is that, and sigma, yeah. And then that's right, yeah.
Similar.
And that they are. And then
I admit I was thinking
alpha.
Sigma.
Alpha, beta, oh, got pressed. Damn it. Beta, gamma.
I read a memoir by the guy responsible for the equation editor in Microsoft Word and its update for years and years. He was like, yeah.
That's amazing. Alpha, beta, gamma, delta. What's next? Come on, guys. After delta. Gamma's before delta. Alpha, beta, gamma, delta, epsilon. There's also one called, is it upsilon? It's really funny. Epsilon. Yeah, but we're not at theta yet. Oh, there's phi, theta, mu, nu, omicron, omega. They have omega, in other words, big O, and omicron, small o. Which you'd think I'd know how to spell, but I don't.
The negative slash shortcuts are handy. You can do there for us.
Yeah. Not nice. I'll tell you, the equation editor, it's a beautiful thing. Anyway, there we are. Note which reaction is exothermic and endothermic in the examples above, and the gap between the two energy levels represents the change in enthalpy. So I want you to draw an energy level diagram for the reaction of magnesium and oxygen with delta H. And again, look, guys, look here. See how here it just says the word reactants? If you're doing a real one, what would you put there? The reactants. And then it says the word products here, but of course, if you're doing this for real, what would you put on the other side? The products. And should you still balance it? Yes. Okay, so go ahead and do that. Make me an energy level diagram. Howdy. Do you want to start helping me get set up? We're going to do heart dissections today.
I know.
In bio.
I know.
So, I need to put the heart guy. I will. But we also kind of do that. You don't mind if I will like heart stages back. Can we think back there? Yeah, we'll be buckets. Sheep hearts and big hearts both are cool. They might not be buckets. They might be back sealed. I can't remember, but I know they exist. They might be in bags. Back in like the box or something. They definitely exist. Back into the lab. Back into the lab, and then vowels back there. So these things kind of trays, scissors, both like just all stuff you know. Yeah. Not sure this happens. Okay. Trays are up on the shelf of room 14. And then paper towels are here. Let's make sure we put paper towels under any of the trays because They leave those awful wax, tar residue. Dissecting hearts today. Bio.
Whoa, which like human?
I don't. They don't give me human hearts, but I've got some sheep hearts and some pig hearts.
That's good. You get some false readings for human heart because it's deceitful of all things.
This is true.
I can't tell if you're focused or you're looking at it like.
Is he grading your work?
Yeah.
The first one.
How's she doing?
Decently.
That's good.
Probably perfect on the 2 out of 5.
There you go. That's pretty good.
So decent. That's what.
What does that mean?
What did you want? You wanted incredible, best I've ever seen. Holy crow! How'd this kid do so well?
Perfect question mark.
Perfect question mark. Perfect exclamation mark. Maybe instead of reprinting, I'm just going to have you come up and make up a random number for everyone on that page rather than waste the paper. That feels trashy. Is that trashy?
You can just fix it in your computer and tell us.
Yeah. Okay, who's got this for me? What do we got? What's this going to look like? Is this reaction endothermic or exothermic?
One of them is exothermic.
This one's exothermic. So that means, and of course I'm going to use a ruler always to make nice straight lines because I'm not an uncultured Nacolturny heathen. And is it going to look like it's exothermic, so we're releasing energy, so it should look, I don't know, something like that?
Yes. But like the product line.
Oh, you're good. You're good. Look at you. If it's exothermic, then we're starting off with more energy, and we're ending with less. By the way, I would prefer that you give it a gentle curve, not the hard straight lines that the example does. We'll call this time, and we'll call this what axis? The enthalpy axis. All right, and then what is our reaction? What's going to be in the reactants? Magnesium is what? Mg. And oxygen is O2. And then we need to figure out the formula. And of course, magnesium wants to give away how many electrons? 2. Oxygen wants to take how many electrons? 2. I don't even need to do any work here. What do we notice about that? It is a good fit. So what's the formula going to be? MgO. Nice. Is this balanced? How would I balance it?
Putting it to Mg and MgO.
They're found, I don't know what hearts these mammal.
Yeah, those are they.
And then these are pickles.
Yeah, so they can both go back there. Thank you so much. So 2 magnesiums and 1 oxygen, diatomic oxygen, will give us how many MgOs? 2. All right, cool. And then if we wanted to indicate delta H, we would note that that is the change in enthalpy right there. And of course, in this case, the change in enthalpy is negative. The enthalpy is going down. This reaction, I mean, we don't know the scale, but this reaction looks like one that happened fairly quickly. Of course, that depends on the situation. If you take magnesium and you light it on fire, you will basically get this reaction. It burns very quickly. Did you do that in grade 9 science? Probably. Did you hold up a strip of magnesium and light it on fire? Did you not? Everyone get to the back. Everyone get to the back. Get to the back and get a lighter. Do you know where the lighters are kept?
I didn't watch it yesterday.
Sorry?
You'd think Mr. Leonard was teaching instantaneous rate of change with all the tangents.
I like it. I like it. That was good. Sinead, do you want to get a Bunsen burner going then?
Mr. Leonard, how many trains do you want?
I don't know. Like how many groups do you think we'll have in that bio class? They got to be at least 3, so no more than 10. So let's
Can
get
we
10.
be in a group of 4 or 5?
No, I'm fine with bigger. I'm not fine with smaller.
Okay,
Made of money here.
Okay.
So let's get 10 trays back there.
Yeah, because we were originally going to have 2 groups of 3, but Hannah's not here, so I'm messing with our plans with like lab partners, and then we were going to have 1 big group.
Sure. Yeah, that's fine. That is. burnt magnesium? For God's sakes, that's ridiculous. Alright, stop spinning that. What do you think you're in the Wild West? Is that what you think? You're a cowboy? I don't know. Maybe turn the gas on? Maybe turn the gas on.
He said that you
So
could
valves. Physical valves. Open up.
He said that you could just take it.
Perfect. Yep. Awesome. And do you have any pair of scissors on the desk?
Yeah.
You. Now, switches up, green buttons. Are we happy with that? Hold on. Are we happy with this? There you go. Oh, what was that? What do we like in place? Flame in place. Then.
Where on your desk are the scissors?
Push it forward. I mean, you objectively did, right? Shut the gas. That one, you can't necessarily open all the ways.
Is it like in a drawer or something?
Out.
So we're putting more gas before you open.
Yeah, gas all the way. That's all.
No.
That's all.
Under papers.
Okay, shut the gas off. Shut it. Okay, as previously discussed, you can't open it all the way. You're gonna have to open it a little bit, but not all. Okay. Quiet, you. You don't criticize. I criticize.
I'll just go get scissors from your room.
Don't worry about it. It's fine. I got hands.
I'm sorry.
Okay, let's burn some magnesium.
Sorry.
You can go ahead and do so. Rule is this: when you burn the magnesium, if you leave it in here, it will actually burn fairly slowly because it's competing for oxygen with what? Okay, there's a lot of gas coming through. So when you go to burn your magnesium, you want to put it in the flame until it gets hot enough to burn, and then you want to take it out. Then you need to promise you something, which is you're not going to look at it so you don't go blind. You can look near it, but you're going to be bright. All right? Does everyone promise me they're not going to go blind? Like you will seriously, you can do retinal damage. Don't stare. All right? Well, good. Yes, I'd like to worry you. So I'd like you not to stare at it so you don't do retinal damage.
What's the maximum?
Just shut up. Honestly. That's such a great 9-boy question. You're like, this thing can kill you. You're like, okay, what's the closest I can come? Talk to me. Like, just, come on. Come on. Yeah, how about it? What else? Again, now we can give it a bit more oxygen because it was. You just gotta get it lighting. So just do the tip and then take it out once it's hot. 3, 1, now. There you go. There you go. Yeah, I wasn't kidding. Was not lying. You gotta do it. You do it again. Yeah, go ahead, grab these. That's the reaction. So you can see that time frame is pretty accurate, right? When you burn it, it releases energy fairly quickly. You seriously never did this in a lab? Wow. It's like a fun lab. Do not blind yourself. I will blame Trush. You don't want to get Trush in trouble, do you? Ventilation's on. I feel like the exhaust is not moving like she normally would. Right? That does not seem like it's moving towards the like it.
Go far away. I go to the end.
That's a lot of smoke.
It this all the time.
Mr. Orlando.
But listen, this puts the alarms off. That's their fault for not giving me proper ventilation. I refuse to take responsibility.
Is there a vent over there?
Yeah, no, we have ventilation. It's this, and it's supposed to suck the air into here. But does not seem to be sucking the air into here, and I'm wondering if they've disconnected it up top. Because these things usually really go. It's a huge air handler on the
Could
roof.
be the first test of our sprinkler system.
I don't think there's water in that yet. We're good. Yeah. Yes.
I don't think the trays are. There's still paper towels in my
Who?
How did
Wasn't
Wasn't
do that?
Green.
I'll help you. Do you mind getting started? Just get some gloves on, dude. I'll come help you. That's super good. That's true. In the course? Yeah.
Burn her entire assignment.
I will.
I do that a lot.
I don't.
So this is actually how
See yours.
camera flash bulbs work.
Oh, you
This is our magnesium ribbon. Let's go on
This
this.
is-
Literally sitting next to the big. In the old days, if you ever seen them using flash bulbs and the bulb would fall off and break and they put another one in, it was single use. This film was so slow to go to the light. They had to make it really bright light. So you see like people getting the photo taken with a flash bulb, so like these places, they're like incredibly like sunshine and bright. I don't know blind, but I'll tell you, even in the 90s, cameras were a lot less sensitive, so the flashes were really bright. So when taking a photo, there's a lot of photos of people going like, this.
Red eyes.
Yeah, that's the right eye. Blasting on the Alright, we took the gas off, shut the valves, press the safety. So that's that one. So that's magnesium oxide. That's magnesium. That's magnesium. One of them, yeah. When you see the whites, that's magnesium. No, maybe not. Oh, yeah. Alright, let's see. Oh, I do not think. I think they have disconnected my ventilation duct up there.
Breathing particle magnesium
That's fine. But could we open the window? That's annoying. They could have told me, hey, we're turning off your ventilation.
True.
That would have been useful information.
We're all gonna get magnesium.
It's probably also why it smelled so bad in here on the organic lab day.
That's what I was gonna say. I'm like, that smells stuff around.
Which it normally doesn't. The ventilation in here is pretty serious, actually. Like, it usually works pretty well. Okay. Shh. Listen up. Your assignment, I'm going to need you to bring up to me. I'm just going to make up numbers for the back page rather than waste paper. And then I can suffer the slings and arrows when I have to mark them all. Give me a second. Just give me a second. I don't know what I want. What do I want? A what?
A cup of coffee.
I've got a cup of coffee.